Okay, so we'll talk about vehicular wireless networks. So vehicular wireless networks are also known as ad-hoc networks. Sorry, VANET. VANET is vehicular ad-hoc networks. So we'll talk about their architecture, their applications, requirements, routing, etc. Then we go into one particular standard, which is called Dedicated Short Range Communication, DSRC. I mean, basically, it's not really a particular standard, but this is a particular band which has been allocated for vehicular networks. And then we go to a particular standard, which is 802.11p. For 11p, then we talk about 5 MAC and products and so on and so forth. So, vehicular networks could have communication between vehicles as well as communication with the units which are on the road, fixed units on the road, roadside units. And it is clear that in either case, the topology is changing very fast. The cars are going at 30 miles an hour at least, if it is in the city. And so the distance between the cars and the distance of the car from the roadside units is changing, dynamic fast speed. So that is one thing. Second thing is that we are not as energy constrained as we are in a mobile. On a cell phone, battery is the issue, but in the car, battery is not the issue. Location-based information. And second thing is nobody is interested what is happening in the rest of the world. They're interested right now what's happening in the road at this minute right here around me. And so you're interested in congestion information. You're interested in finding a hotel near you, or a store near you, or a coffee shop near you. And then so it's mostly location-based and accidents, etc. Right? Delay constraint. And obviously, the information has to be right now, not yesterday's information or this morning's news. We need it now, what things that happened a few minutes ago. Varying environments, city streets with all buildings versus open highway road. So as we go through this, we will see that city problem has taken precedence, and all the solutions that are there right now are more for the city streets, and open highway is probably the future. And the cars have lots of sensors. So anything that you need, you can get. GPS, speed, proximity, engine, temperature, wind speed, everything is available to you right there in the car. All right. So that is the good and the bad. The good is that we have no energy problem. The bad is the speed. So there are two issues. One is how do we talk vehicle to infrastructure, V to I, and second is vehicle to vehicle, V to V. And there are two units. They are called RSU, roadside unit, and onboard unit is on the car. So there is something on the car which is OBU, and something on the road which is RSU. What is the kind of information that you need? First is you need infotainment. Infotainment is information and entertainment. Entertainment information, navigation information, telecommunications. So that is all under this infotainment. Telecommunication is actually sort of not an issue right now because we all do talking from the cars. But we want to minimize the driver distraction. And therefore, what we really need to use is Bluetooth and voice navigation. So we don't want them to be punching keys or pressing the buttons or touch. Touch is basically also prohibited in many situations, but minimize the touch. So for example, in my car, I can't set the destination on the GPS while it is running, while it is driving, and I have to stop it and then say, okay, I want to go here. So that kind of limitation. They don't want distraction. Bluetooth. Yeah, of course, Bluetooth is good because then, you can just talk to the car with voice recognition. Traffic control is the second application, is that the government wants to reduce the congestion. It's good for people and good for the environment. So basically, infrastructure will tell you right before. Nowadays they do with the boards, but it could be much faster and easier if you could just get the information from the cars. Right, the second it happens, some car could tell you that okay, there is an accident, and you don't have to take that road. You just change your route and things like that, right? So highway advisory radio about congestion, warn before dangerous curves and road conditions, and navigation based upon congestion. So basically, you could get, some of it is happening right now, but it is still not as dynamic as you would like to have. So you could get congestion information on your GPS nowadays. But again, that takes quite a bit of time because this information has to go to the headquarters of the GPS company, and then from there it will be broadcast. So generally it is more like an hourly report rather than minute report. Safety. And so that's another thing, is that we really want to use wireless to avoid crashes. So things like adaptive cruise control, and these things are already being advertised. I saw some advertisements on the TVs. But they basically, you maintain distance from vehicle ahead. So, actually there's not too much of wireless required for this. This is more of a sensing issue. But, wireless could be used as well. Right? Forward collision warning. And so basically this is related to the same thing, is that you measure the distance, and if the distance is decreasing very fast, you apply the brakes automatically. And speed regulation. So right now you can do the speed limit, but what would be good is that, and this is the problem with the speed limit right now, is that if the person ahead of you goes 1 mile less, then you have to remove the speed limit and go ahead of them and cross them and all that. So with this, you could just go with the flow. All right, so we know that this is very useful. And so what are the requirements for designing a network? First thing is that there are some messages which are highly critical. So there is a high priority here. See, in other applications, the priority may not be that strict, but here, for example, the collision is going to happen in 3 seconds. Right? You cannot wait, put into the queue, and so that has to just go. So that is the thing. So low delay, several milliseconds. Electronic toll collection. So if you're going through a toll booth, you have to send a message to the toll booth. Toll booth has to take your credit card number or whatever that is required, and then say, okay, all right, you're ready to go. All that has to happen while you're driving at 30 miles an hour, and so there is a very strict time limit there. Roadside service locator, if you're looking for a gas station, it's good that if you find it, within few milliseconds. So all that is very highly critical messages. But then there is a lot of non-critical messages, such as video entertainment, so that is one thing. So basically there are two kinds of messages, critical and non-critical. So we have to have very strict prioritization. Second thing is range is very small. So these guys are designing right now for 300 feet, which is basically inside a city, where you need to know something which is very close to you. Mobility is given, so I don't have to say much, everything is moving. And security is important because somebody can give you a wrong message saying that there's a congestion and make you take some other route. Somebody may become the roadside unit and give you even other messages. Privacy, somebody could find out where you are driving if they can figure out from your beacons or things like that this is the car belonging to the governor. Yeah, go ahead.
Even though this appears purely ad-hoc, is there like a PCP or maybe some type of infrastructure coordinator that?
Okay, so it's coming up. We'll see that in a minute as to how this is done. But this is more ad hoc than what we saw in the 60 gigahertz stuff. Privacy. So you don't want anybody to know your location, your ID, your credit card things, right? Even though they're exchanging all this information. And you don't want anybody to change any of those information either. All right. So with these, there's a lot of work going on in the last several years, and now there is a standard. So we can talk about that. Security requirements, talking more a little bit, is that multi-hop communications, there is a collaboration required. So if I want to get to that car, and there are two cars in between, my message will go to the first car, they'll have to forward it to the second car and third car, and so on and so forth. So there is some kind of collaboration required. There has to be some kind of decision on the part of the intermediate drivers whether to waste their energy on forwarding or not, right? So that's the second issue, autonomy. And autonomy is everybody has a freedom to decide whether they want to participate in helping out, whatever you are doing, right? But it's a multi-hop communication, and there is the issue of autonomy. Authentication. Obviously, if you are going to believe something, you have to know whether it is coming from a believable source. Accountability. Accountability is if something wrong happens, then you can go back and see who did it, right? So the messages that impact the network functions should be audited. They should be logged, right? And deliberate disruption should be penalized. Otherwise somebody could just stop the whole traffic. Privacy. So we already talked about that. Location, name, type, vehicle, etc. should not be disclosed. Availability, and if the network is down, the vehicle should still be working, right? So with that, the routing is slightly different than normal routing that we do in the networks. First of all, there is a lot of broadcast. A lot of messages are not going from A to B. They are going from A to everybody, right? Whether it is the roadside unit or whether it is a car or anything else, there is a lot of broadcast. Then there is a special kind of broadcast called geocast. So there is a broadcast, but we don't want to send it to the other roads. We just want to send it to Highway 64, within 300 feet of me, right? Why do other people have to worry about, what is happening on this place, right? So it's a geocast, geographically limited broadcast. Forwarding, obviously, we talked about multi-hop. Clustering. So sometimes we want it to limit to a group. Police. So this is a message only goes between the police, or between the fire, or safety, or within police, fire, and safety. So that is a limitation right there. Beaconing. So basically, there are some messages where, one person says, well, this is what is happening, and then other person, adds their own experience to it and says, well, I think this is what is happening, and so on and so forth. So this is called beaconing. Beaconing is that you take the previous information, add your own piece, and then you forward. So you modify the message by your own knowledge. Position based, which is same thing as geographical. So basically, that's another thing, is that your routing cannot be address based. It has to be location based. So for example, if I want to go from A to B in IP routing right now, we just have this routing table where we know that everybody who's going to that address has to go through this router, this post, right? But here it is different. Everybody who's going to that car has to go through this car, right? This second. Next time, or maybe that car. So it's all who is next to me, right? So the routing is, whole algorithm is different. Delay tolerant. So delay tolerant is that if there is no next car, but you still wanted to go, you could just hold on to the information. That means not just the source, intermediate points. So if I want to send, if the RSU, the roadside unit, wants to send some information to a particular car, then the intermediate car could just hold it in the buffer for some time until that car comes in the range. That is called delay tolerance. That means store and forward. And so this store and forward is different than normal router store and forward. I mean, normally the routers don't really store it. They store it into the memory, and as soon as possible, they get rid of it. But here, they might even store it on a disk. So that could be few seconds, milliseconds, days in some cases. That is what delay tolerant is. Ad-Hoc. And obviously, everything is mostly ad-hoc, okay? Because there are RSU, so RSUs could act like an access point, but mostly the network is ad-hoc because car to car, B2B. So basically, there are many technologies which can be used inside the car. First is DSRC, Dedicated Short Range Communication. And for that, there are few standards such as 802.11p and IEEE 1609.1.2.3.4. And then, so they work up to 1 kilometer at 200 kilometers per hour. And I think that number 200 kilometers, I personally don't believe that 11p will work, but I haven't done the testing, and I don't know if anybody else has done the testing. I looked at the design, and it looked like the design will not work, but that is not something that I will stand behind. Anyway, so that is the number that is given. WiMAX, which we are going to learn later on, is a metropolitan area network, MAN, where you could go to several kilometers. And so that can be used directly from V to I. A WiMAX tower could just broadcast to all the cars for several kilometers. 3G could be used, a cell phone, just broadcast to all the phones, or to a particular phone. And then satellite could be used. But we will not talk about those three in this lecture. We'll just stay on this new thing, which is 11p. First of all, spectrum. So the government has been working on creating this, making this possible. And what they have done is they have allocated a 5.85 to 5.925. Okay, so they have allocated that band exclusively for this one, DSRC. All right. So even though it is allocated, it is not that somebody has to pay for it. Nobody pays for it. It's free, but only you can use it for this purpose, not for anything else. So basically the community got together and then they created 7 10 megahertz channels. So you can see the channels here. This 5.85 gigahertz is here and 5.9 is here, and then basically they have created channels which are numbered as 172, 74, 76, 78. So again, the channels are numbered even number because they're 10 megahertz. 5 megahertz would be each channel. So if you want to do 173, just like we had it in 2.4 gigahertz, 5 megahertz is the numbering system, but usage is 10 megahertz. Right? Out of these 7, first is not used and the last is for the future. So then there are left 5. Out of the 5, the middle one is what they call CCH, control channel, and the other 4 are what we call service channel, SCH. So the control channel is the one that everybody has to listen to, as you can think, basically, and then basically figure out what they're saying. And if they say, well, listen to channel 174, then you go to 174 and listen there. Okay. So service channel is generally for data. Actually, you can do data on CSH as well, but again, control takes precedence. So basically, control channel and the service channels. Now, HAL 184 is reserved for future high availability, low latency data. Something that is real time, low latency, but has to be available all the time. That means very low utilization will be used in 184. Right now, it is not designed or used. 172 we said is not used. Now, different EIRP for classes. I have made slight changes in that slide and that line. Then after your handout was printed. So basically, there are 2 limits: 33 dBm and 43 dBm. And the idea is that government can use 43 dBm. So police, fire, safety, they can use longer range. And everybody else has to do 33 dBm, 10 dBm less. Okay. Actually, that applies to both OBU and RSU. So basically, on both sides, if it is a government vehicle, they could use 43 dBm, and private vehicle have to limit to 33 dBm. And obviously, I don't know how many private RSUs could be, but there could be private RSUs. So for example, okay, so the example of private RSU is a gas station could put an RSU you would just stop by and then get internet access and then get out, right? So that's the roadside unit. And hopefully you will get some coffee or tea, and so they make money out of that, as well as maybe internet as well, who knows. So that's an RSU. And obviously government RSU would be, if they're going to give you some tourist information, that could be done by the government, right? So there are RSUs. Private RSUs can use only 33, and the government can do 43. Any questions so far? All right, the protocol. Now that looks a little bit complicated. So basically what they have is two planes, data plane and management plane. The data plane, and by the way, this was designed initially by ASTM, American Society for Testing and Materials. You can look at the two slides together, the picture and the next slide. ASTM designed this whole thing, and they were hoping that they will not really need to go through IEEE in some sense. But anyway, so they designed one protocol, which is called, and they actually created the word WAVE. Okay, so the WAVE is wireless access for vehicular environment. And so they had the thing called Wave Short Message Protocol, WSMP, designed by ASTM. And so then it goes through LLC, logical link control, goes to the MAC layer as one would think, and then it goes to the PHY layer. PHY layer is the 11P. MAC layer is 1609.3 and 1609.4. So much of it actually went without going through the IEEE 802 committee as much as they could, and then finally they came here. But so this is 16.09 is another group. Even the IEEE 16.09 is another group, and they felt that 802 ideas will not apply, so they just try to use as much as possible their own thing, and then there are a little bit of 802 here. So starting from the top, you use UDP or TCP. Obviously, TCP is not advised because you don't have time for three-way handshake and things like that. You just make a request and you get a response. That's the best thing. So UDP is mostly it. You get a short message from WSMP. But if you're coming from UDP or TCP, then you have to go through IPv6. So IPv4 is out. And particularly, the idea here is that every car could not really get an IPv4 address for any meaningful communication. And so IPv6 addresses are easy to find. So IPv6 and this short message, they will go to the logical link control, which could be as well as null, which is mostly it is. And then it goes to the MAC layer that we will talk about in a minute. And it goes to the PHY layer, which is IEEE 802 11P. On this side, there is a management entity. So anytime you want to do much of anything, you have to go to the management and tell that, look, I want to send a message of this priority, and then they will know that that is a priority. So basically this is slightly different than what one would have done. But anyway, right now, lot of information about transmission. So actually they call it management. I would have called it control. There's a lot of information which is required for transmission goes through this part here. Okay. So if you want, just like I said, the priority of your message, you have to just first tell it here and then it will be used here. Then it goes to MLME extension. So basically MAC layer management entity. So this is MAC layer management entity already exists. 802.11 already has something to manage the MAC layer, right? But since they didn't, they really needed something more, so they had two parts on management of MAC layer. One is MAC layer management extension and one is MLME. All right. For PHY layer, they used standard PLME, which is the physical layer management entity. And then they added security on the side here. Wave Security Service Entity, WSE. Now, so we'll go through some of these in detail. But basically, just things to remember is that only IPv6 and are the short messages, and then there is a new MAC, and there is a new PHY actually, and then there is a whole thing of management which you have to know about so that you can tell these layers what to do. Okay. One thing which we haven't talked about is that the packets contain priority, data rate, and power. So this is another interesting thing I found, in the sense that generally we leave the physical layer to decide what is the right QAM rate, or what is the right modulation, whether you should send it at 54 or, not 54, 27. So the physical layer can come up and down in the rate, right? But here the application layer tells it that this is the rate you should send it at. And power basically says that, just send it at so many dBm, and therefore it will reach only so far. So if you want to send it very far, you increase the power. If you want to send it just very close, you decrease the power. So these are application layer decisions. All right. Then WME, the management entity. WME is this one. This one registers the priority, data, and power for different applications. So when you start an application and you say, well, I want to do, let's go back to that RSU. RSU wants to start an internet service. RSU wants to start a video service. For each application that is running on the RSU, it will register with its own WME, saying that this is the priority for this application, this is the data rate and power. Okay? And then Wave Security Entity. I don't know whether this is incorrectly printed in your handout. Please check, because I found that there was something wrong. So Wave Security Entity, few extra characters got in between WA and Wave. So Wave Security Entity does data encryption and key management. So there's not much to talk about there. That's the standard data encryption. All right. So the PHY. PHY actually done by 802.11. And so these are the same people who designed the rest of the 802.11. And so they just took it and modified it slightly. So they just took it 11A. 11A runs at 5.8 gigahertz. To switch it to 5.9 gigahertz does not require too much work. Right? So they took 11A, and 11A uses 20 megahertz channels. To switch it to 10 megahertz channel, again, doesn't require too much work. All right? So they took 48 data, 4 pilots, and 12 guards of 11A and kept it here for 10 megahertz. And this is where people could disagree. And I'm sure there must have been a lot of discussion about this before, is that now the carriers are very close to each other, closer than before, because at only 10 megahertz you have 64 carriers. Previously in 20 megahertz we had 64 carriers. Carriers are very close to each other, and therefore the delay spread is an issue. Because what happens is, if you remember Doppler shift, if you're moving very fast, the Doppler shift is large and the carrier could become here and there, right? So generally what we do is, and I actually was involved with design of the plane communication, not with the car communication, plane communication. So I looked at in this detail, when planes are going at 600 miles per hour, actually that is probably the lowest speed, 1,000 miles per hour and so on and so forth. Then it becomes really a big issue, because what is your Doppler spread? So you don't want to keep carriers very close to each other. So I was really surprised here that They took 11A, which was not really designed for anybody running fast, and they took it and put it into 11P at the same number. So anyways, that's my personal disagreement with that. But anyway, so the idea is subcarrier spacing is half that of 11A. You understand why, right? You take 10 megahertz divided by 64, as opposed to 20 megahertz divided by 64. And because of that half, all the parameters, all the time stuff has to be doubled. So symbol size is twice, the guard interval is twice, and so multipath can be basically more, and the data rate is half. So instead of 54, you get 27. So that's very easy to understand. This diagram actually is same as 11A, except that from beginning to the end it is 10 megahertz. Okay, the next slide summarizes this. 11A, 11P, 5.8 to 5.9, 64, 64, number of subcarriers is same, data carriers is same, pilot subcarriers is same, bandwidth is half, the symbol duration is twice, guard time is twice, and so on and so forth, preamble is twice. So on the time domain, you just go half the rate. On the frequency domain, you just go half the distance. Yeah.
Do we need a license for using this spec?
Do you need a license? No. So the thing is, every car, hopefully, when it is implemented, will come built in, just like it comes with FM radio, AM radio, and the user doesn't worry about it. The radio station needs the license, but here, I don't think the RSU unit will need a license. Yeah.
In terms of the IP addresses, will it be dynamic or just like a worldwide?
Okay. Everything is country specific. So this is all US specific. I'm not talking about Europe. I'm not talking about any other country. And this is the problem, because I'm not sure where 5.9 gigahertz is available, where it is not available. There is no worldwide standard for anything. Okay. And so, I mean, that is one thing, is that if you go into the books or anything like that, they will describe you different countries, this and that, and it becomes confusing. So I just want to keep it to the US right now. And in fact, in the next lecture as well, because every country has slightly different. And the manufacturers have to struggle with that, basically, to somehow make a device that works worldwide. Generally, it could be a multi-band device or multi-thing device, where everything, you have to just turn on the EU mode or US mode. And it's like television. You cannot use the television from here in Europe, right? PAL system versus whatever we have here. And TSC, ATSC. Okay. So this is 11P is very similar to 11A. That's what you have to remember, okay? Moving on. Let's go a little bit up, which is the MAC layer. And so that is where the DSRC starts. So there are two channels we saw, control channel and the service channel. Control channel is for safety messages and network control. So obviously network control, but if something has to be done in the next 1 second, it can go to the control channel right there. So all devices use CCH and one or more SCH. Two types of devices, multi-channel devices and single channel devices. Some devices are single channel. That means they have only single radio, and they will listen to CCH, and then they will go to SCH when necessary. Otherwise, they will stay in CCH. So they kind of switch between SCH and CCH as required. Same radio. Then there are devices which are multi-channel, which can use CCH and SCH at the same time in parallel. If you remember the radio chains, right? Remember when we talk about MIMO and the radio streams, how many streams you have? That radio chain is what we are talking about here. How many channels you have? All right. So most of the time we assume that the devices could be single channel, and therefore whenever there is a allocation or anything like that, you need the time to switch between the two channels, and there is a guard time between the switching. I thought I had a picture somewhere, but I don't. So you need a guard time for switching. All devices must monitor CCH for a common CCH interval. So just like any other place, basically we have a super frame or a frame, and that repeats every so often. The first part of it is for control part, right? That part everybody has to listen to the control, just like a beacon. And all devices should synchronize the clocks to UTC time. So that is another thing. So how do you know when is the beacon beginning? Everybody has to synchronize. And you can do that very easily if you have a GPS, which most things have now. Even watches have GPS. Of course, GPS has GPS. So basically, the GPS is kind of taken for granted. If not, you could listen. Say, for example, if you're inside a building, you could, well, how will you driving inside the building? Maybe. So let's say you're inside someplace where GPS is not available. You could get it from the RSU. The roadside unit could give you some timing signal. Generally, RSU will have GPS clocks and transmit it in their beacons. So you just align to that particular bit when they say, okay, begin. That's the time beginning. So everything is synchronized. And you have a group called Basic Service Set, BSS, which was called, what was called, we had used another name, Video BSS before? Video Area Network, huh? PBSS. Now it is WBSS. That is, W is for wave, Basic Service Set. So in one network, you have Basic Service Set. And obviously, neighboring BSS will use different service channels. So remember, there are 4 service channels and 1 control channel. So everybody has to use the same control channel. And if they're going to use the same control channel, they will have to offset it such that they don't come into the communication, the control interval of one into the other, right? All right. Now, 2 kinds of traffic we know, IPv6 and WSM. And the packets contain the channel number, data rate, power level, and priority. The IPv6 stream now doesn't have all this, right? WSMP packet can have that right there, but IPv6 streams don't have any place to put channel number, data rate, power level. That's why they go through the management stack. Okay. So they tell MLME about their profile. That includes the channel number, data rate, and power level. So now you see here, MLME, this extension. The IPv6 will tell here that I need this messages to go, basically whenever the application starts, it tells that this is the thing I need, and that is the one that is used here. Okay, for IPv6 it comes to like that, for ASTM and for, WSMP it comes straight through. Now, 11E had 4 queues. So this one has actually 4 queues per channel. So if you have 5 channels, you could have 4 times 5. If you have 1 channel, you could have just 4 queues. But if generally people will have 2 queues, 1 for CCH, 1 for SCH, you will have 8 queues. But this is 4 channels per 4 queues per channel. And so there are 2 units called channel router and channel selector, which are in the next slide. So channel router directs the packet to the right channel and queue, and the channel selector monitors the channels and schedules the transmission with a specified power and data rate. So let's look at this picture here. I've shown here 8 queues, 4 for 1 CCH, 4 for CCH and 4 for 1 SCH. 2 channels, right? 4 queue each. So which channel you go through is decided by this channel router and which queue you go to. So this basically either talk to MLME or it gets in from the packet itself. From either way, it knows what channel and what route you are going, what queue you are going through, and it puts into that can. Now, once you get to the head of that queue, and the channel selector decides which queue will go next and which channel will go next and which queue will go next. And once you get to the head of your station, then there's the external contention. That means second car, third car, fourth car. So that basically is this is the internal contention, internal scheduling here, and this is the external contention there. Right? So this is finally the packet is ready to go out of this car, but it has to decide, and that means it has to get scheduled. And we're going to talk about that in a minute. But basically, so that was the external contention. Any question about this?
But
Yeah.
priorities between these two, because the safety messages should have higher priorities, and they have 4 separate queues.
Yeah.
So is the priority built in that these 4 separate queues have higher priority than the other 4?
I don't know. I don't know. I think here at least there must be one which is really urgent, like we saw very critical messages. So that has highest priority among all the queues. But I don't know with the second queue here and the first queue there, I don't know the relative.
Just select the
That could be as simple as just the policy driven, They could just get out of this and say, okay, your policy. Okay. But it is not necessary that the CCH always has priority over SCH. So some queues have priority over other queues. And so all it is saying is that even in the control channel, you might have packets which are of different priority. Okay.
Who makes the internal scheduler? Is the channel selector or?
Yeah, so basically, this is okay. So there is a queue 1, 2, 3, 4, right? For each of these queue, now if you remember 802.11e, there is a TX op, there is a DA, whatever that is. I mean, AIFS. All of those things basically decide who gets next. So all of those parameters are here, except that there are many times. Now, one more thing I should say that many of these things are designed but never used, because, who's going to decide whether this second queue is, second queue is better than this first queue, and people don't have 16 queues in their brain and they can't. So a lot of things are designed, but at the end, they are not used. So how many have you bought a router? So you bought a wireless router. It might even have a feature which says that, okay, QoS enabled. So you go there and QoS enabled. Then it asks you, next question, it asks you, so which computer you want to give the priority? That's the maximum I can do, is that basically I can say, okay, let me give my priority to my laptop and not to somebody else's laptop. That's all, right? But after that, how do they decide, TX op and things like that is just too much. But if somebody wanted to go through that, they could do it. So right now there are 4 queues per channel, and then for each queue you have all those parameters that we had before. SIFs, diffs, piffs, whatever, so many things, right? So that continues, and then based upon that, somebody comes ahead and one packet goes out. All right, WBSS formation. So any wave device can start a WBSS. So this is what the question we was asked. Is there a access point? Obviously, if there are 5 cars standing in a parking lot, there is no access point. Right? So any car can become like a PCP and can start a WBSS when requested by an application, which means somebody presses some button in the car and says, okay, announce this, or do this, or ask this, so they can start a WBSS. And that becomes a provider, a PCP. So the device that starts the WBSS can become the provider, and it could be an OBU or RSU. So it doesn't really mean that the RSUs always are the access point. Okay? The main difference is that RSU generally have more storage, more this and that, more power. And generally they're stationary, so, different kinds of application, but either one could become a provider. And it generates the announcements. And everybody else who joins later is called user. Now, so it could be a persistent WBSS, which means it stays little persistent, means it stays for some time. So it is announced every sync interval. So remember that period where everybody, has a beacon in the, not beacon, there is some announcement in the beginning. That is where you say, well, this is a persistent WBSS. Obviously, if something is decided by RSU, started by RSU, they might have a persistent WBSS. Otherwise, most of the time, these are non-persistent WBSS, short-lived, announced at formation only, easy to support an on-demand file download, and then they're gone. All right, two cars want to exchange something. They start it, and within a few seconds, they're gone. And then they will probably form WSS with somebody else. So that is persistent and non-persistent. Several applications register with WME with a provider service identifier, PSID. PSID is similar to the port number. When you register on port 80, we assume that you are providing a web service. When you register on port 21, we assume that you're doing a file transfer protocol. Similarly, there is a PSID which you register with your management entity and you say, well, I want to provide this thing. And basically, there has to be some standard and some non-standard, just like the port number, so that people who are looking for that service can actually ask for that number. Right? Is that point clear? How PSID is used? A WBSS is initiated when the first application registers. So if there is no application which is using any wireless, of course, there is no point in creating WBSS. But if suppose somebody says, I want to provide a web service, all right, then they register with the management entity, and then a WBSS is created, and then it announces it, and people come and join and leave and so on and so forth. The provider service table is broadcast periodically. So the provider which started it has all the services in a table, and it announces that, okay, I can accept port 80, PSID 80, PSID 21, and so on and so forth. So these are the services I'm providing. All right. And if you need that, then you just connect to it. It is what? Local port number? Yeah. So here's the thing. When you go to a web service, web service is my computer providing web service, right? Port 80 belongs to my computer, not that computer. So every computer has a port 80. This computer also has a port 80, right? But that is the web service on that computer. So what it is saying is that this provider is saying that I am going to provide this, here's the table for that service. So it is local to the extent that it is just into that particular host. Yeah.
Once it registers your port number, you drive into the city, does it announce it constantly?
Yeah, it could drive, announce it constantly. So if you are in a parking lot of a garage, of a gas station, it could announce that we have internet service available here for you. Right? Or we have pizza available. I don't know. They might have some kind of announcement for that as well. So that will be constantly, RSU will be constantly doing it. And I can imagine that, for example, a police car driving on the road could be announcing that it is a police car and please get out of my way. Right? So there are, now I haven't seen the standard table, PSID table. So I don't know, but the usage is very similar to the port number. The user applications register with their interest in their WME. And now this is an interest. So the user, whoever is interested in web service, will say to a WME, like, I'm looking for a web service, right? And so obviously it will start looking for web service. So WME monitors the announcements and check to see if a PST, the service table, provider service table, has this thing that they're looking for. And if there is no active application, then the PBSS is shut down. So basically, when the web service goes away or whatever started, the last application resigns, just the PBSS is gone. There is no announcement to be made, nothing to be done. I mean, the shop closes for the evening, PBSS goes away. Non-WBSS communication. So now if you want to go to non-WBSS, then this is called OCB mode. OCB stands for outside the context of a BSS mode. OCB mode, outside context BSS. So a station do not have to be a member of BSS to transmit. So this is like ad hoc mode. You know, in the A22.11 we have ad hoc mode where you can just send a message to a neighbor. So that's the kind of thing. So this is called OCD mode. Station do not have to be a member of the BSS to transmit. A wave device can send a WSMP message to a broadcast address on CCH. Right? You can just broadcast to the world that I am a police station, a police car, whatever, right? Like that. Another wave device can respond to this message on the CCH. And for this, no BSS advertisement or synchronization is required. Timing advertisements from the provider, default parameter values, and timestamp in reading local time. So the provider is the person who starts this transmission, OCB mode message. So they will have something before it which will say, well, here's my message starts, here's how you synchronize to it, and this is the parameter value. Authentication handled by higher layers. So now anybody can announce that I'm a police car, please get out of my way. So they have to make sure that this is a police car, and so there is authentication to be done. But that is handled by the higher layers. OCB stations use slightly higher AIFS than WBSS members. Higher AIFS means what? Anybody knows what higher AIFS means?
So more the duration.
They have to wait more.
They have to wait more.
Yeah.
The priority will be lesser for this.
Exactly. That's the point. So the BSS people get priority. OCB stations use wildcard in the BSS ID field in the MAC frames. So, I mean, basically, in the MAC frames, which actually we haven't seen so far, there is a field which says this is for this BSS, because we could have many BSS in the same area, right? So that is null. Null is wildcard. Okay, so basically, luckily the products are coming in. I haven't seen a car with 11P, but I can see here the chips. So Arada system makes OBU and RSU, and these are the pictures from Arada. Roadside unit and the car unit. The Coheda Wireless produces the radio, which is shown here. NXP produces the software-defined radios for this radio, and we will actually describe software-defined radio in the next lecture, so I'm not going to spend time right now. And then Unix makes the OBUs. The company Itium has HDL implementation. They just sell IP. You know, so if somebody wants to make a chip, they can buy the IP from them and then make a chip. Everybody knows what is HDL, right? Hardware description. So then we have card access engineering product designs, and now they help you in the product design. LightPoint does the platform, test platforms, and they make the signal generator. So there are many companies which are into this thing. And so this is actually in some sense a little bit more real than many things we saw last time where they were not real. So the future is that DSRC is actually right now as it is designed is for short range communication and for a smaller speed. I think all that numbers we saw for the decreasing the number to half, all that will work up to certain speed, and the distances are also short, 300 feet. But on the highway, 300 feet could be very small distance. And so this is good for the city. Long range communication is also required on the highways. And now how do you do? I mean, if you want to find a let's say gas station. In the highway, 1 mile will take 1 minute, right? So you really need to find very fast, and you need to reach few miles, before. So you need some long distance technology. So cellular could be one of them, and that means that you will have to have one OBU for the city, one for the highway. That is why we might need a multi-channel OBU. But this is all future. Nobody is talking about it right now. Let it first come in the city, then we worry about extending it. All right. I haven't seen a car as yet for 11P, so maybe they're putting it in some cars. I have seen advertisements for crash prevention, but that doesn't really require wireless. All it requires is a sensor. You just get the distance, and if the distance is decreasing, you apply the brakes. All right, that brings us to the end of this module. VANETs have a dynamic topology, very tight delay constraint for critical messages, and then you could have V2V or V2I communication between RSU and OBU. All of these words now should make sense. What is V2V? What is V2I? What is RSU? What is OBU? DSRC uses 10 megahertz channel with OFDM in 5.9 gigahertz, CCS for control and safety, and SCS for all other messages, right? So 10 megahertz. Now ASTM started Wave with Wave's short message service, and the 802.16.1 through 4 did the MAC for the DSRC and MAC management and security stuff, and then P is the PHY. All right. So that's another interesting thing, is that unlike many other 802.11s we have seen, well, 60 gigahertz was different, because 60 gigahertz we had a MAC and PHY, everything from 11. Here, just the PHY is provided by the 11. And then the QoS is similar to 11E, but 4 queues for each channel. All right. Reading list. I have put these 2 things here. It says must read. So it's a 12-page, 14-page paper. I found it really easy to read. You must read that one, and then this book. There are lots of references. All the standards are here, but these are more for reference when you need it, but not really for anything.